Hi everyone, welcome to lecture 20, which is the second lecture we'll see on the probability calculus. The objectives for this video are the following. So after watching, everyone should be able to, number one, define the probability calculus rule for conditional probability. Number two, define independence. And number three, derive the special and general probability calculus rules for conjunctions. Okay, so last time we looked at the probability calculus rules for negation and disjunction, as well as the special kinds of statement tautologies, contradictions, logically equivalent statements, and mutually exclusive statements. In this video, we'll define another rule for conditional probabilities, and using that, we'll derive the general conjunction rule. So first, to conditional probabilities. If P and Q are statements, where P of P is non-zero, we write this thing. P of Q given P, where I'm reading the vertical line as the word given, to mean the probability of Q on the condition that P. So what does that mean? Conditional probabilities allow for the fact that if a certain statement P is known to be true, then knowing P might affect the probability you assign to another statement, Q, and this may be different to the probability we assign to Q alone, just probability of Q, P of Q. So we define conditional probability in the following way. Let P and Q be statements with the probability of P non-zero. Then P of Q given P is equal to the probability of P and Q divided by the probability of P. Now we see now why we make this stipulation on P of P being non-zero. If P of P is 0, then the right-hand side of this expression is undefined, so we only define it in cases where P of P is non-zero. Now notice that just like in the case of the general disjunction rule from the last video, we've still got this P of P and Q, so the probability of P and Q, floating around in the expression, which we haven't defined yet. So before we look at some examples where we apply this rule, we're going to define this thing. So when we apply the rules, we know precisely what's going on. So to define the general conjunction rule, we first define this notion of independence. To do that, let's look again at the expression for conditional probability, which was this thing. Now let's suppose P is a tautology. So let's pause for a quick question. Well, if P is a tautology and Q is a statement, then the probability of Q given P is the probability of Q on the condition that P. But because P is a tautology, it's true no matter what. So the probability of P of P, is equal to 1. And if we substitute 1 in for the denominator on the right-hand side, our expression simplifies to this. P of Q given P equals P of P and Q. The next thing we notice is the following fact. If P is a tautology, which we're supposing it is for the moment, then the statement P and Q is logically equivalent to the statement Q, and this can be checked using truth tables. So if P is a tautology, our expression simplifies again. We can replace the right-hand side with just P of Q, because P and Q are logically equivalent when P is a tautology, and we know that logically equivalent statements are assigned the same probabilities. So now if P is a tautology and Q is a statement, then the probability of Q given P is just the probability of Q. This means intuitively that learning P tells you nothing about the probability of Q. It's just assigned the same probability that it was when you didn't take into account whether P obtains or not. Now this fact serves to motivate the following definition. We say two statements P and Q are independent just in case P of Q given P, the probability of Q given P, is equal to the probability of Q. The idea behind independence is what we just said. Learning P tells you nothing about the probability of Q. Now, we've got enough on the table to define the special conjunction rule at this point. So recall the definition of conditional probability. If P and Q are statements where P of P is non-zero, then P of Q given P is P of P and Q over P of P. Now if we multiply each side of this equation by P of P, we obtain the following thing. P of P times P of Q given P equals P of P and Q. Now we suppose that P and Q are independent. By definition, that means P of Q given P is just P of Q. Now substituting P of Q in for P of Q given P into that expression, we've proved the following rule. Proposition 1 here, which says that P of P and Q equals P of P times P of Q for statements P and Q. I've also just swapped the left and right hand sides here, so the thing we're deriving is the thing on the left, the probability of the conjunction. And this is our special conjunction rule. It's special because it only holds for independent statements P and Q, and it tells us how to calculate the probability of the conjunction P and Q using the simpler probability of P and the probability of Q. Notice also something a little bit subtle. In order to derive this from the expression used for conditional probabilities, we assumed that the probability of P was non-zero, but the special conjunction rule, P of P and Q equals P of P times P of Q, holds whether the probability of P is zero or not, so we don't actually need to assume that P of P is non-zero in the proposition. Now while our reasoning goes through for cases where the probability of P is not zero, what's really needed to finish the proof of proposition 1 here, i.e. of the special conjunction rule, is to show that it also holds when the probability of P is zero. And that's a gap you'll fill in the assignments, so I'll leave that issue to one side here. So we've got the special conjunction rule. The general conjunction rule is something actually we've already seen. It's this expression. P of P and Q equals P of P times P of Q given P, which we obtained by just rearranging the conditional probability formula. So without any stipulations on P and Q, except for the probability of P being non-zero, they don't have to be independent, P and Q. This is the rule that allows us to calculate the probability of any conjunction P and Q. Now, you might think there's something a little bit weird going on here. So we've derived a general conjunction rule, that's proposition 2 on the screen, and we've said that the probability of P and Q is the probability of P times the probability of Q given P. But by definition 1, from a few slides ago of conditional probability, we said P of Q given P is P of P and Q over P of P. So how are we supposed to calculate this thing, P of P and Q, if we're supposed to calculate it in terms of itself? That is, after all, the thing we're trying to figure out. Now, this isn't something we'll have to worry about in practice, because all the examples we'll see, if we want to calculate a general conjunction without restrictions on whether the statements are independent, we will transform the problem into one that involves statements that we do know how to calculate the probabilities of. And that's something that we can do that isn't circular. Now, the reason I'm mentioning all of this is that the examples in the book that claim to be calculating probabilities where the probability of a conjunction is involved, really what's happening in those examples is they are transforming conjunctions into other types of statements that we have rules to deal with the probabilities of. Now this all seems to me like it's a little bit swept under the rug, so I'm not really a fan of the rigor of some of those examples. So let's see what I'm talking about here and have a look at an example where we make this transformation. So first let's look at an example where we calculate a conditional probability. Let's suppose we have a regular deck of cards with no jokers in them. So there are 13 cards from ace up to king of each suit, and the suits are diamonds, clubs, spades and hearts. So that makes a total of 52 cards. The red cards are hearts and diamonds, and the black cards are spades and clubs. Now suppose I have a partner and they pick a card at random, and I'm interested in the probability that the card is a queen. Now suppose further that my partner tells me the card is red. So I've learned the card is red, and I'm interested in the probability that the card is a queen given that it's red. Now, here's the expression governing conditional probabilities again. If P and Q are statements where P of P is non-zero, then the probability of Q given P is the probability of P and Q divided by the probability of P. Now, if we let P be the statement the card is red, and Q be the statement the card is a queen, then we notice that the probability of P is non-zero because there are red cards in the deck. So we can make sense of the conditional probability that we're interested in, and we can say that the probability the card is a queen, given that it's red, is the probability that it's both a queen and red, divided by the probability that it's red. So to calculate the thing on the left, we're going to have to calculate both of the things on the right. The denominator is marginally simpler to figure out, so let's do that first. That is, let's calculate the probability that the card is red. Now we know that half of the cards in the deck are red because each suit has 13 cards in it and 2 suits are red. So the probability that the card is red is 26 out of 52, which simplifies to 1/2. Now we have to calculate the probability that the card is both a queen and red, and this is a conjunction. But notice that we cannot just use the general conjunction rule we've specified because that would be circular. We would end up calculating it in terms of the conditional probability that it's a queen given that it's red, which is exactly the thing that we're trying to figure out. Neither can we use the special conjunction rule because we don't know if they're independent without calculating the conditional probability that it's a queen given that it's red, which again is the thing we're trying to figure out. So instead, and this is what the book does but doesn't explicitly say so, we think for a moment about another way of saying that the card is both a queen and red. We know that there are 2 red possibilities, either it's a heart or a diamond. So, saying the card is a queen and red is just the same as saying that the card is either the queen of diamonds or the card is the queen of hearts. That is, these 2 statements are logically equivalent. But one of them, the second one, is a disjunction of mutually exclusive statements. The card cannot be the queen of diamonds and the queen of hearts at the same time. And we know how to calculate the probability of mutually exclusive disjunctions. That's what we saw last time. To do that, we just add the respective probabilities of the disjunctions. So let's apply that. The probability that the card is the queen of diamonds is 1/52. And the probability that the card is the queen of hearts is 1/52 as well, because there's only one of each of that type of card in the deck. So we see that the probability that the card is either the queen of diamonds or the queen of hearts is 1/52 plus 1/52, which is 1/26. Because the 2 statements, the card is the queen of diamonds or the card is the queen of hearts, and the card is a queen and it's red, are logically equivalent, we see that the probability that the card is a queen and it's red is also 1/26. They get the same probabilities. Now again, this is why I didn't think the examples in the book were super illustrative. They purport to be examples in which you calculate the probability of conjunctions, but when they're explained, really what you're using is the disjunction rule for mutually exclusive events and logical equivalence, not the expression we gave earlier, which was the general conjunction rule. And since we're in the business of rigor in this class, I wanted to point that out. So, we can now calculate the conditional probability that we're interested in. The probability that the card is a queen, given that it's red, is 1/26 divided by 1/2, which comes to 1/13. Okay, now let's look at a super simple example involving the general conjunction rule where we won't have to count cards. I'll leave applications of the special conjunction rule to the assignments, so get some practice in there, and remember to check for independence if you think you ought to be applying that special rule. The general conjunction rule we said was this. For statements P and Q, where P has non-zero probability, the probability of P and Q equals the probability of Q given P times the probability of P. So let P be the statement, the weather reporter forecasts rain tomorrow, and let Q be the statement, it will rain tomorrow. Suppose the probability that it will rain tomorrow, given that the weather reporter forecasts rain tomorrow, is 0.9. And suppose that the probability that it rains tomorrow is 0.5. Then here is a question, so have a little scribble just before we go through the answer. So, what's the probability that the weather reporter correctly forecasts that it will rain tomorrow? Well, the statement that the weather reporter correctly forecasts rain tomorrow is logically equivalent to the statement that the weather reporter forecasts rain tomorrow and that it will rain tomorrow, because then they will be right. And this is a conjunction. Now, since we know all the relevant probabilities, a straightforward application of the general conjunction rule, where we suppose, of course, that the probability that the weather reporter forecasts rain tomorrow is non-zero, says that we multiply the probability that it'll rain tomorrow, given that the weather reporter forecasts rain tomorrow, and the probability that it will rain tomorrow. So we multiply 0.9 and 0.5, which any Google calculator tells you is 0.45. Okay, so that's the last of the examples in this video. So we've seen the conditional probability, special conjunction, and general conjunction rules, and this means we've covered all of the elementary rules of the probability calculus that we'll need. Now there'll be plenty of practice using these rules in the assignments, so we'll leave it at that here. Next time we'll be looking at this thing called the expected value of a gamble, where we'll put some of our work on probabilities to good use. So have a go at your self-reflection questions, and I'll see you all next time.